Assalamualaikum wabarakatuh, and very good afternoon to everyone. So today we're going to talk about analysis of a single queue where job arrive at they have only a single queue, meaning that job arrive at one job at a time. Okay, this is what we call analysis of single queue. I will touch a little bit on analysis of multi-queue, but the basic, the fundamental single queue, which you can expand to do analysis of multiple queue. Alright, this is simplest queuing theory, analysis of single queue. We learned before Little's law and then candle notation. This is like the second part of the queuing theory. So this is the overview. First, we're going to go about birth and death processes. So jobs arrive one at a time and not as batch. So you have here lambda naught is the arrival rate, and I have mu is the service rate. Okay. So state the number of jobs in the system. So this is state 0, and then this is state 1, and so on. So jobs can go from state 0 to state 1 or going back from state 1 to state 0 depending. So if like arrival of new job changes the state to n plus 1 or birth. So from state 0 to state 1 it will become n plus 1 or birth process. But if like 1 going back to 0 it will become n minus 1 or a death process. So if you go from state 0 to state 2, in order for you to go back to state 0, you have to jump like 2 times or 1, or it must be a similar. So from state 0 to state 2, if you want to go back to state 0, you must jump from state 1. You must jump back to state 1 and state 0. You cannot jump like, okay, let's say you want to state 0 to state 100. So you have 100 jumps. In order for you to go back to state 0, it must be something like 100 or 99 or maybe 101. Must be around that area. You cannot like state 0 to state 100, 100 jumps of state. It cannot be like, if you want to go back to state 0 from state 100 to state 0, it cannot be like 50 or something like that. It must be like around 199 or 101 or some number of that. It cannot be a different. This is for the system to be stable. We assume that system, in order for system to be stable, there are certain balance condition that we must follow or we must obey. So all this is a state transition diagram here. Now you can model is j minus, this is a birth and this is a death process. Whenever state move a new jobs changes, moving from state to the next state, it will become a n plus 1 birth. But whenever the departure of jobs from my current state to current state j minus 1, it will become a death process. So when the system is in state n, it has n jobs in it. Okay, when the system is in state n, it has n jobs in it. The new arrivals takes place at the rate lambda n, arrival rate. The service rate is mu n. So meaning that the jobs coming in L, let's say L naught is so we say L1. So the new arrival takes place is Ln, and then L1, and then you want the service rate is mu n. How long it will service the job until it depart from the service or server or something like that. So Ln and mu n. So we have here the arrival takes place lambda minus 1, lambda 1, and the service rate is mu 1. Okay, and then we assume that both the initial arrival times and service time are exponentially distributed. Okay, what does mean exponentially is you remember the Poisson process. You have average arrival time, but it's not really the same. So this is exponential, random. So the theorem, a state probability is that the steady state probability Pn of a birth death process being state n is given by Pn. You have a arrival rate, a dot product over a service rate, of course a dot product times probability of the state is probability of state 0. Okay, so this is the dot product. Sorry, this until this part is a dot product. Okay, L0 until L minus n and mu1 until mu n. So here P0 is the probability of being in the 0 state. Here is P0, P1 and so on. Okay, suppose the system is in state J at time t. There are j jobs in the systems. In the next time interval of very small duration delta t, the system can move to state j minus 1 or j plus 1 with the following. Okay, you have here, this is a state diagram. You have here I, state I, then you state I plus 1 and I minus 1. So in order for state I plus 1, so j, so sorry, j, we use j here, j, sorry, j plus 1, this one j minus 1. Okay, j minus 1. Okay, so probability of j plus 1 is this one. This is the probability of j plus 1, something like that. This one. Probability of j minus 1 is here. And probability is stay at j is lambda j delta t. This one is mu j delta t. Okay, it j move to j plus 1 j, and when it stay, if it stay at j, state j, it is 1 minus lambda j delta t minus mu j delta t. Okay, alright, this is the proof. This is the first step of proof. So you have a state diagram. From state j move to j minus 1, you have mu j delta t. And if you want to move into j plus 1, you have lj delta t. Okay, lj delta t. And if you want to stay at state j, here you have minus 1 minus lj delta t mu j delta t. You want to stay. So you have here, this one you want to stay at j, this one j plus 1 and j minus 1. Okay, so moving to j plus 1 is lambda j delta t, and moving to j minus 1 is mu j delta t, and to stay here is 1 minus lj delta t minus mu j delta t. Okay, if there are no arrivals or departures, the system will stay in state j. Okay, state j here, j plus 1 and this one j minus 1. Delta, let's assume that delta t is very small. There will be a zero probability of two events, two arrivals, two departures, arrival and departure occurring during this interval pj. So interval pj probability of being in state j at time t. So we assume that delta t is 0 and there is a zero probability of two events, two arrivals, two departure, arrival, departure occurring during this interval. So the way we write the equation is this one is P naught t plus delta t. So we assume that delta t is small and zero probability of two events, two arrivals or two departures, or arrival or departure occurring during this interval pjt, during this interval. So we can write p probability of being state j at time t. We can write 1 minus for p naught is t plus delta t, 1 minus l naught delta t p naught t plus mu 1 delta t p1 t. I will not go details on that. So this is a 19th century mathematician, Markov. So P1 delta T, P2 T plus delta T, and so on until Pj T plus delta T. So again, this is a transition diagram. J want to go to J plus 1. Okay, P, J plus 1, P, J minus 1, and this one is P, J. Okay, probability J plus 1, probability J minus 1, probability of J. Of course, you add delta T here. And then the equation above can be written as follows. If you put a limit minus pj, you have, if you differentiate, you put a limit here. This is the equation. This is the same, you put a limit or you differentiate dpj over dt time. So we have this final equation here, lj minus 1 pj minus 1 t, and then uj plus lj pjt uj. So what you have here, because delta t is small, so you eliminate delta t from the delta t. You put a delta t limit to 0, and then you divide by delta t, so delta t can be cancelled. Okay, delta t can be cancelled. All delta t on the above side can be cancelled. So you have here lj minus 1, pj minus 1 t until pj plus 1 t. So under steady state, okay, remember everything must be in a steady state. We assume that it's a steady state. Pjt approaches a fixed value pj. That is, if you put a limit t to infinity, you got a pj. And when you differentiate this equation pj, you will get a 0. Okay? You will get a 0. So substituting this in the jth equation, because dpjt, okay, dpjt is 0, so you substitute the equation 0 on the left hand side, and you have this. And then if you rearrange pj plus 1, you will get a p1 l naught minus mu1 p naught. Okay, l naught mu1 p naught. You have a pj plus 1. If you want to use p1, probability at state 1, at state number 1, you have p1 l naught over mu1 p naught. But you want to, if like the solution, if you want to have a pn, you have l naught until ln minus 1, u1 until u1. This is a dot product, which you can use pi times p naught. Sorry, you can use a pi symbol. This is the dot product, not the pi t.142. This is the dot product of L and mu. So n is 1 until infinity. So this is the dot product. So this is a proof. We are not going through that unless you are mathematicians. You can do all this. There are a lot. I mean, there are 3 to 4 pages to prove this. Okay. So the sum of all probability must equal to 1. If you rearrange here, you have 1 over 1 plus a dot product lj uj plus 1. So this is the sum of all probability must be equal to 1. If you rearrange this, you will get this equations. And then mm1q, the exponential with single q. Okay. One server q is so this is the q, the most commonly used type of q, used to model single processor system or to model individual devices in a computer system. One server, one counter, and anything that one only have one. But this is a fundamental. You can expand from single queue to other multiple queue. Assume that the inter-arrival times and the service times are exponentially distributed and there is only one server. So this is a memoryless, exponentially distributed following the Poisson process. No buffer or population size limitation, and the service discipline is first come, first serve. So this is the assumption of MM1Q. No buffer or population size limitation, meaning that buffer is, we assume that buffer infinite, but in the real world, the buffer is not finite. We will see about this in the examples. And we need to know only the mean arrival rate L and the mean service rate mu. So remember the basic of queuing theory. L is inter-arrival rate, mean arrival rate. where the unit is in s minus 1, and then the service rate also s minus 1. State is the number of jobs in the system. So you have 0, 1, 2. This is a state diagram. Again, this is state diagram here. Of course, here we start with L0, L0, L1, L2, and then this one is mu1, mu2, and mu3. Okay, service rate must start from 1. L0 because you can start in initial, you can start with L0. So state number of jobs in the system, jobs 0, state 0, 1, 2 until j plus 1. Because this is Lj minus 1, Lj minus 1, and so on, Lj plus 1, Lj plus 1. This is mu j. Okay. Birth death process start with ln. N is 0 to infinite, and mu n to 1. So because this inter-arrival can stay with state 0, meaning no jobs whatsoever in the server. If service rate doesn't have a state 0, because you to service anything you must have a job, so it start with 1. Okay, service rate must have at least 1 job, so no state 0. L is the arrival rate, meaning that you can start with state 0. There is no jobs or no number or no whatever packets or no stuff in the system, no anything in the system. The system is 0, no waiting jobs, so you can start with state 0. So probability of n jobs in the system, you can have Pn where lambda over mu to the power of n. Probability of n jobs, let's say 13 jobs, put there 13. P naught n is 1, 2, and until infinite. So the quantity L minus U we call a traffic intensity or busy time or whatsoever. Some call it busy time, non-idle time, utilization rate or whatsoever. Okay, traffic intensity, utilization time or something like utilization rate, something like that. It's not really correct to say utilization of system. Okay, traffic intensity L minus U, and it denoted by symbol rho here, rho. So this is a symbol probability, this is probability, and this is symbol rho or traffic intensity. Forgot how to spell rho, never mind. So this is traffic intensity. So this is the probability at state 0. This is probability at state n. Okay, so n is between 1 to infinite. So this is a Pn is Pn over Po. So this is a probability of n is to the rho to the power of n times P naught, or you can also 1 minus rho times Pn if you try to expand this equation. And then n is geometrically distributed. So this is the number of system in n. So the probability when the state of n is increasing, the probability will be decreased in the exponentially or geometrically distributed. Okay, from this one, this is called geometry distributed is also called exponential distributed. So utilization of server is probability of having one or more jobs in the system. 1 minus P naught or rho. 1 minus P naught or rho. Probability of having one or more jobs in the system. Okay. So lambda minus mu. So this is called mean number of jobs. Rho over 1 minus rho. and variance of number of jobs in the system is rho over 1 minus rho to the power of 2. Okay, so just this is symbol of rho. This is symbol of rho is different from the symbol of probability. Probability is here, P. This is rho. So this is all the MM1Q single Q analysis equations. Okay, so these two is the most important, arrival rate and service rate, traffic intensity, rho, and all this is the equation. Some of the equation is probably have zero jobs in the system. This is important. Well, n jobs in the system, Pn is also important. And then you have ER, this one also important. Okay, in the exam you'll be given this formula. I don't expect you to memorize this one. Another is probability of finding n or more jobs, Pn, n or more jobs. So this is so important, this is important, and so on. Mean busy duration. So this will be given during your examination. So we go for the example. On a network gateway, measurement shows that the packets arrive at mean rate of 125 packets per second. So this definitely, this is lambda is 125 packets per second, and the gateway takes about 2 milliseconds to forward them. Gateway takes about 2 milliseconds. So service time is 2 milliseconds is 0.002123, yeah, 0.02 second. So see, lambda rate is always s or s minus over s or s minus 1. The time is always unit is second. Using the MM1 model, single queue, analyze the gateway. What is the probability of buffer overflow if the gateway has only 13 buffers? Okay. Using the M1, analyze the gateway. So you have your L, you have your S. Mu is 1 minus S or 1 minus 0.002. Okay, arrival rate 1 to 5 per second. Service rate 1 or 500. 500. Service rate is 400 packets per second. And you have gateway utilization. Remember, pel lambda minus mu, or lambda is 125 over 500. So you have 0.25. Okay, you have 0.25 lambda minus mu. And probability of n packets in the gateway, just refer to the equation. Probability of n packet in gateway is 1 minus rho to the power of n, or 1 minus 0.25. 0.25 to the minus of n is 0.75, and 0.25 to the power of n. So you get this equation. So lambda is rate is 125 per second. Service rate is 1 over s. Mu is 1 over s. Okay, service rate. Service rate mu is reciprocal to service time. Okay, service time and response time is different. Okay, service time, how fast you can do jobs within that server, or within that systems. So mean number of packets, you just use this p rho to 1 minus rho, and then 1 minus mu over 1 minus p, and so on. So probability of, okay, what is the probability of buffer if the gateway had only 13 buffers? So more than 13 packets in the gateway, you have to use rho p to the rho to the power of 14. You meaning had 370 times 10 of 4 packets per billion packets. So this is the probability of buffer overflow. 4 packets per billion packets, or 4 times 10 to the minus of 9. Okay, so 4 packets per billion packets. This is the notation of the probability. 4 packets per billion packets, or 4 times 10 to the minus of 9. To limit the probability of loss less than 10. Okay, the next, what is the next questions? Okay, you have this one. And what is the probability of buffer if the gateway had only 13 buffers? So for more than 13 packets, so you just use the equation, row to the power of 14. I think this is the row to the power of finding n or more jobs in the systems. Okay, so you have 4 packets per billion packets, and to limit the probability of loss to less than 10 to the minus of 6, sorry, to get packet below 1 packet per million. So you have here, you use the same, but in order for a buffer, you must have, okay, if you have 1 jobs, you want to limit, if you want to avoid buffer overflow, how many buffers? So you always use notation n plus 1. Okay, you have 1 jobs and how many buffers you have here. So basically you need about 9 buffers, but if you give like 10 also, it's like 9 and more. So if you give 10 or 9 or 10, it will be a correct answer as well. All right, to limit the probability of less than 1 to the 10 to the minus of 6. Okay, so the last two results about buffer overflow are approximate. Strictly speaking, the gateway should actually be modeled as a finite buffer mm1bq. But in a single queue, we assume that buffer is infinite. Of course, in the real system, you must have a finite buffer. However, since the utilization of the system is low, and the number of buffers is far above the mean queue length, the resulting are close approximations. Okay, the number of buffers is far above the mean queue length. So, mean the buffer size is far more bigger. So we assume that it's infinite. So the result obtains a close approximation. So let's say here you have example number 2. The average response times on the database system is 3 seconds. You have R over 3 seconds. So just remember that R3 is a response times, not a service times. During a 1 minute observation interval, the idle time on the system was measured to be 10 seconds. So utilization is 50 over 60. So the idle time system was measured to be 10 seconds. Using MMR model, determine the following. So given ER is, so if you have ER 1 minus mu, ER is 1 minus U over 1 minus P, Y minus rho. So system utilization is straightaway 5 over 6. You can put it here. So ER is 1 minus mu over 1 minus rho is equal to 3. Alright. You have here. So rho is 5 minus 6. If you want to find average service time per query, service times 1 over mu is, you solve this equation here. Y minus mu is equal to 3 times 1 minus rho. So 1 minus 5 over 6. So equal to 3. 6 over 6. 6 over 6 minus 5 over 6. So you have here 3, you have 1 over 6. So you have average service time per query is 1 over half a second, 0.5 seconds. So this answer is 0.5 seconds. Average arrival rate. So this is pretty straightforward. You have mu. Mu is, if 1 over mu is 0.5 or s, mu is 1 over s, or 1 minus 0.5, you have 2. So average arrival rate is 2 jobs per second. So En, you can just rho minus rho is 5 over 6 times over 1 minus 5 over 6. So let's see the answer. You have 3, correct. And then you have 55 over 6. Oh yeah, so I forgot 2 times 5, 2 times, okay, 2 times 5 over 6. Okay, so the answer will be 1.67 jobs per second. So arrival rate. So important for you to know the lambda and the arrival rate and the service rate. So R, this is the response times. The service times is different. Okay, if service time is different, response time when you arrive at the counter bank, you take the number waiting time, and then when the counter bank, when the person that the counter person call you, this is where the service rate started. All right, so this is example 2. So if you want a multiple M, can be single, double, or triple Q. This is the equation. Much more, it is much more complex. So for single Q, this is single Q, and this is the multiple Q. So we will not cover multiple Q. I just show you the equation of that. So yeah, that's it for today. This is the last lecture about the Markov chain. You just can read the slide by yourself, and it will not be covered in the final exam, the Markov chain. But of course, if you want to know further about the Markov, the single Q analysis, more advanced, you can study the Markov chain. Okay, thank you very much.